Thank you for reminding me. I appreciate that. Okay, so some of this is laying the groundwork. Some stuff we just talked about, and some of it will follow directly. What's wrong with the following statement? Because the digits 0 through 9 are the normal results from lottery drawings, such randomly selected numbers have a normal distribution. No, they wouldn't have a normal distribution. That would mean one of them is the highest, the one that's most often chosen, and they're sloped down. But that's not true. They actually are uniform. Since the probability of each digit being selected is equal, they're equally likely, so it's uniform. So a lot of people get confused about uniform and normal. So that's just a warning to us. Which is the shape? I've drawn it a few times. D, yeah. And which is the correct for standard normal? It's up on the board. Standard normal is the Z.
0, 1.
Yeah, mu 0, sigma 1. Okay? And okay, so this is a special notation, Z alpha. Remember, alpha is the level of significance. Alpha is equivalent to level of significance. And I think I told you that it takes on usually 3 different values. It's either 0, 1, 0, 5, or 1, 0. Although sometimes it can be 0, 0, 2. So that's the level of significance. That's what goes in the tails. And so when you see Z sub alpha, it's definitely a positive number such that alpha is in the right tail. So if you have the curve, if this is alpha, then this number is Z alpha. That's what it means.
Okay.
And if you want it to be negative, you have to force it to be negative. So that would be minus Z alpha. And then this would be alpha in this tail. As far as area, I'm signifying area. But when you see this, it has to be positive. So this is the only answer. But it's always symmetrical. The bell curve is symmetrical, always symmetrical. In terms of probabilities, in terms of the numbers that describe those probabilities. We're going to be doing 2 things. We're going to be finding probabilities given a Z or eventually X values, or we're going to be given probabilities and we're going to figure out what the Z or the X is. It goes 2 ways. And from now on, alpha, or not alpha, but probabilities will always be 4 decimal places. The Z's will be either 2 or 3 decimal places, so you could distinguish which one you're dealing with. So Z alpha denotes a Z-score with area of alpha to the right, to its right. You'll see that coming up. We're going to have icons. Okay, but first we got to do the uniform and get it out of the way. Just a couple of questions. Now there is a uniform calculator. We can use it. It's real easy. We might as well. So I'll open up StatCrunch. And if you look under stat calculators, you got the uniform. And what you have to do is you have to put the lower limit and the upper limit, and then you have to put X is either less than or greater than, or you can do between 2 numbers. You see, it's right. It's standard means you can be X less than or greater than. Between means X is between 2 numbers. So you can use it either way. You just have to set that up. So the first thing you do is put in the limit. So this is 0 to 8, right? Lower limit 0, between 0 and 8. It says, find the probability a randomly selected passenger has a waiting time greater than 1.25 minutes. So I just put in X greater than 1.25. That's the 3 decimal places to be 0.844. Okay. Now you could have done it on a calculator too. You could say Okay, greater than 1.25. So 8 minus 1.25 divided by 8, because it's 8. So there it is. So that's all we did. We just took the total area in the red and divided by the 8, because that's the total area is 1. You see, if you go from 0 to 8, look at this. The probability is 0.125. Because the base times the height has to equal 1. A valid probability distribution always has to have a total probability of 1. And now you can see in the drawings of the uniform, it's going to be obvious. Okay, so that was, we'll do one more of these, number 8. Statistics professor plans so carefully that lengths of her classes are uniformly distributed between 45 and 55. So 45, 55. And find the probability given class runs between 50.75 and 51. So between, see, I took the between one instead of the standard. And so the lower one is 50.75. The upper one is 51.025. Right? See, it shows you the area. Between those two numbers, that's the area. So once again, we're equivocating area with probabilities. And now we get to the normal. Here's your normal curve, the icon. So there's your z value. They want to know what's the probability that z is less than 0.75. Okay, so now I close this one and I open up the calculator for uniform. Or, I'm sorry, no, I keep saying that. Normal. Now the first thing, it's always queued up for the standard, 0, 1. Later on, we'll change it as accordingly, but right when you open it up, that's what it comes from set as. So we want x less than 0.75. By the way, it says x. It should be z because it's 0, 1, but you can't change it. So you just have to realize that it's not an x, it's a z. And so we do x 0.75. All right. So you can see I generated the same pictures they gave me. At 4 decimal places, 7734. Okay? Pretty easy, huh? Number 10, now we're going the other way. We want the probability that z is greater than minus 0.95. Notice when z is negative, you're to the left of the center. Right? Because when you're to the left of center, z goes negative. So now I do x greater than negative 0.95. I got the same picture, so it's 8289. All right. And now I think we'll do a between. Yep. See, now we're between two numbers. We want to know the probability between those two. So I do the between up here. That cues me up for between. On the left, I have negative 0.7. On the right, I have 1.27. So 7058. So it's kind of mechanical right now. Number 11. Now they're giving us the probability. They're saying that this probability in this, for this value of z is 0.9838. So it's less than. So I got to go back to standard, choose less than, and then I go over here and put in the probability of 0.9838. now instead of putting in the z value, I'm putting in the probability. When I hit compute, it gives me the z, and I get the same picture. So that area matches that area, and so the z that we want, the 2 decimal places, 2.14. We used to have to do this by table. That's what this is up here. Since I know I'm to the right of 0, then it's going to be positive. So it's page 2. I'll show you what it looks like. It's ugly. This is what we used to have to do. So I have to find 9.838 on here. I'll just show you how crazy this is. 9838. There it is, right there, 9838. So you get 2.1, and this is the 4 column, I think. Let's see if that's right. Yeah, 4 columns. So 2.14. That's how we used to have to do it. I just want to let you know what these are. The books all the textbooks used to have those in the back, all these tables. We don't have them anymore because we have machinery. Although they still give us the tables. I guess it's a throwback to somebody who still wants to do it that way. 15. Now to the left, so I'm going to do greater than. I want my z greater, because it's greater than z, right? So greater than. So that, I don't know what the number is, but I know the probability. The probability is 8790, so that's what I put in there. So 0.8790. It's minus 1.17. And I was expecting a negative value, right? Correct? Because up to the left is 0. That has to be a negative number. All right. Couple more here. They'll give us some icons. We have to figure out what they are. Well, here's another one. So this one's going to be positive, so it's greater than. I'm already set for greater than, so all I got to do is change the probability to 0.1515. So 1.03. All right. Number 19. So which one is it? It says, assume it's 0, 1. That just the first 2 sentences are setting us up that it's 0, 1. It's a standard, normal. Find the probability a given score is less than 2.14 and draw the sketch. A. Yep. You agree?
I do.
I know, I heard you.
Okay.
Now, what's the probability? So I want it less than, so I got to turn this around, less than. And I want the z value, 2.14. So 9838. Put a decimal point, of course. Number 32. We'll skip a few of these. I think some of these are yours. So same setup, 0, 1, between minus 2.18 and 3.83. Between negative 2.18 and 3.83. A, B, C, or D?
A.
You agree? Yeah, it's A. Between. This is not between, this is not between, this one is not between either because it's got the left tail filled in.
Well, is D a real thing, or is that just...
No, it's a mistake. It's a distractor.
Yeah.
All right, so between, I got to go up here and change it to between. On the left, I put negative 2.18, and on the right, 3.83. It's going to be a large number, 9853. That's 32, 33, less than 3.71. That's easy, right? A. Only now I gotta go back to standard, less than 3.71. It's gonna be almost 99. Yeah, look at that. Like,
Why were the numbers -3 and 3 chosen? Or is that just kind of picked out?
what's that?
The numbers -3 and 3, why those ones? Or is that kind of just
I mean, those,
correct on the bottom? Yeah.
they're just trying to trick.
No. On the actual graph.
Oh, those are 3 standard deviations either side.
Okay. Gotcha.
Yeah. They don't show it all the way out to
Yeah.
371. That's your standard.
Okay.
It doesn't change. Yep. Okay. 38. I think. All right. So they want the P13. Remember what that means from when we did position? 13th percentile. That means 13% of the values are less than that number. So which one would it be?
Probably B.
Yep. 13% or less than that. So that's it. Very good. So what do I do here? I know I want Z less than, but I don't put in the number. I put in the percent. I put in 13% for the probability, and so that's minus 1.12. 2 decimal places. Negative 1.12. 13. Actually, if you round it correctly. 40. Okay, they want to draw the graph that find the density scores that can be used as cutoff values separating the lowest 10 and the highest 10. B. All right. Now, you can do this. You can do this for one, like the upper one, and then just use symmetry. I'll show you. Let's just do it. So let's say we weren't sure, so we had standard, and so we did greater than. We put the 11% in the upper. So we put 11% up here. So it's 1.23. So what do you suppose the number on the other side is? This number. Negative 1.2. So what you do is you just go plus or minus 1.23 because it's symmetrical. Now here's the other way you could do this. You could do this between, but now instead of putting 11 on one side, if I put 11 in either side, how much is that together?
22.
And what is
0?
What's that?
0.
No, 22.
Oh, okay. I thought.
And what's the complement of 22? Because see, if I have 11 in each tail, what's in the middle?
0.
What's the complement of 22 subtracted from a 1, from 100? 78.
78.
So if I just go over here and I put in 78 in the icon only gives me the middle. I can't draw the two outsides. Watch what happens. I get plus or minus 1.23. See, I don't get the 11 in each tail. I get this one, which has 78 in the middle. But that's just so I can get both numbers at the same time. And I know that that's 2 times 11 is the complement of that. So you can do it that way too. But what we actually did was Z alpha. That the 11% in the right tail. Then we knew that minus that number is 11% in the left tail. So that's what we did here. We put 11% in each tail, so we put 78% in the middle, and that gave us the 2 numbers. Make sense?
Yeah.
All right. So you can use this to your benefit, however you like. Okay, so here's Z.010. So alpha is 10%. So all I do is I go back to standard, and I go greater than, instead of putting 11% in there, I put 10%. and the Z value is 1.28. So that's the upper limit on an 80% confidence interval. Why did I say 80%? Because a confidence interval is always balanced. If I have 10% in the right, I got to have 10% in the left. So plus or minus 1.28 on the Z gives me a 80% confidence interval. I got 80% in the middle. We just had a 78% was slightly smaller, was plus or minus 1.23. And 80% is plus or minus 1.28. Just trying to show you the. But see here, they asked for Z alpha. That has to be a positive number. I gotta go with the right tail on that one. All right, so 45. About how much is between plus and minus one standard deviation? How much is between, plus and minus one? So between, just put in plus and minus one. Minus one, plus one. On your empirical, it's at 68%. It's actually 68.27 to be more accurate. But we can say about two standard deviations. We'll just change this to a 2. What's it say on your empirical? 95%. If you check it. Here it's got 95.45. But we say it's about 95%. 1.96 would be 95%. Watch. And that's a famous number, 1.96, because that gives me my 95% confidence interval. See? Plus or minus 1.96. But we just round it to 2. We say, there's 95% of the data is between two standard deviations either side. Okay. What about 3? What's it say on your 99.7, right? Actually, it's 99.73. We say 99.7. But you get the idea. I forgot the decimal point. And then what about 3.5? That's just about everything. It's going to be just about 100%. It's 99.95%. But there are outliers. There's always little
guys hanging around.
Pieces of data hanging out there. Okay, so for 0, 1, find a percentage of scores that are significantly high. So we just did this, in a sense, didn't we? So if you forgot what it was, then you just go back to standard and you go greater than 2. And you hit compute. So 2.27 or 2.28. And do I have to calculate it for the other side? How many are less than 2? Same percent, because it's symmetrical. And so how many are not significant? Those are the ones that are in the middle. Remember, significant only happens in the tails. So if I add those two up, I get 4.56. So that's 95.44. We said 95.45 just a few seconds ago, but it's close enough. All right? You get the idea of that? Okay. Which of the following is not a descriptor of a normal distribution? The graph's bell-shaped? The graph centered around 0? The graph centered around the mean? The graph is symmetric. So A and D are correct. Which one's not correct, or which one's correct from B and C?
C is wrong.
No, B is wrong. It doesn't say standard normal, it says normal. Mu is the mean. It's always centered around the mean. It's just that for the Z, the mean is 0.
Okay.
So gotta be careful, you gotta read it correctly. Number 5. Which of the following does not describe the standard normal? So now we're standard normal, now we're the Z. Symmetric? Yes. 0 mean, S standard deviation 1? Yes. D, the total area on the curve must equal 1? Yes. The graph is uniform? No, the graph is symmetric. trying to fool us. Finding probabilities associated with distributions that are standard and normal is equivalent to well, you can eliminate.
Finding the z-scores associated with the probability.
No, probabilities are associated with area. Area.
Okay.
Probabilities and area are equivalent. Yep. It's okay. It's okay. So now we're going to go to applications involving x's instead of just z's. Once you got the mechanics down, now we can apply it to all distributions. We just have to make sure we get the right mu and sigma. So for the standard, it's 0, 1, right? Easy. Don't miss this one. And what's the dimensions? Or the units? What dimensions do we use on the z? If x is in beats per minute, what's z in? It's a trick question. It's in standard deviations. There are no units. There's no units. Whatever you're measuring your x in, whether it's gallons or dollars, your z-score is just standard deviations. It's distances. So it's unitless. Trick question. Don't let it get you down. Number 6. Okay, so see, this is mean 100, standard deviation 15. So now, first thing I got to do is change it. I got to do the means 100 and the standard deviation 15. They want to know, now, before it was positive, negative, we knew which side we were on. Now we're to the left of 100, so we're less than 100. So we want greater than 85, so x greater than 85. And that would be 8413. I got to tell you, you know what we used to have to do? They didn't have tables for x, they only had tables for the z. So we had to change all these to z-scores and then use the table. So I'd have to change 85 to a z-score.
Which, a lot of math.
Well, yeah, I'd have to do
that whole calculation, right?
Well, I have to do 85 minus 100 divided by 15. I'm using that formula right up there.
Oh, okay. I thought you were.
And those are the z's, not minus 1. So I would go to the calculator or the table, open it up, and find minus 1. That would give me the probability. All right? But this is a lot easier. So between two numbers. So it's still 115. So I'm still queued up for that. I just leave this calculator open. It doesn't have to change. But now I'm between, so I do between. On the lower end, I put 104. On the upper end, 130. And the probability is 3721. All right. Next one.
Let's talk about that purple thing above on the graph in the stack punch. So it's 68, 95, 99.76.
That's if you want to put those in there, I think.
Oh, okay. Fixed on the graph. Got you.
So put them in there.
Okay.
It gave you one. This is instead of 0, 1, 2. Now it's if you go add 15, that's x bar plus x bar plus 2x, or mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. All right.
Okay.
See, otherwise, oh, yeah. Without it, it's just numbers. But if you want the standard deviations, there they are. I never did it before. All right. Okay. That's 2 standard deviations. 130. All right, that was number 8, number 11. So the probability, now they're giving us the probability. Once again, it's 115 mu and sigma, so I can just leave those. They give us a few problems, we don't have to change them. And now we want the probability, so I go back to standard, I want it greater than, but I put the probability in as 0.2317. And compute, so 100, nearest whole number, so 111. Right? All right. That was 10, or that was 11. Number 14. All right, so now let's see, we got to change. As I read the problem, it says the mean is at 104.7, and the standard deviation is 25. And they want to find the probability that a randomly selected adult has an IQ greater than 139.3. So 139.3. 4 decimal places, it'll be 0832. 8%, 8.3% chance. 19. Suppose that sitting back to knee length for a group of adults has a normal distribution of mu equals 22.8, standard deviation of 1.1. So I'm going to put those in, 22.8 and 1.1. So sitting back to knee, I guess maybe they do this for airplanes. Yeah, that's what they say, different places. Okay. These data often used, okay. Instead of using the 0.05 for identifying significant values, use the criteria that an X value is significantly high if it's in the 1% above, and it's significantly low if it's in the 1% below. So we're forming a 98% middle, putting 1% in each tail. See that? So find the back to knee length separating the significant values. So I can do this one at a time. Now, this is the bottom, because it says back to knee length is greater than, so this is the bottom number. This is what? You're forming the middle, low, high for the middle. All right, so greater than 1%, the lower end is 25.4. That's the upper end, my bad. Yes. That's the upper end. The lower end, I have to do less than 1%. That would be 20.2.
Why isn't it good?
What's that?
The number, shouldn't it just be the negative of, oh, never mind, different number.
We're not centered, we're not symmetrical. We're symmetrical, but not on 0.
Okay.
All right, now, watch. Suppose I just did between, and I just said 98%. All I want is the endpoints. See, there they are, 20.2 and 25.4. See them? 20.2, 25.4. So you can do it that way. We build a 98% confidence interval. All we care about is our endpoints. We know if that's 98% due to symmetry, you got 1% here and 1% here. They're just not red. They're white. Okay? Now, is 25.0 significantly high? No, it's between them. It's in the middle. So it's not significantly high because it's inside the range of values that are not considered significant. Anything between these two is not significant. Remember, in statistics, the only time you're significant is when you're in the tails. If you're in the middle, you're usual, normal, acceptable. Okay? Any questions about what I did there? So you could do it both at once. I don't want to confuse you. Or you can do it, but here you don't have the symmetry, you can't do plus and minus, because you just don't have that availability with the way the problem's set up. Okay, 23. These problems get kind of interesting in a way. Survey found that women's heights are normally distributed, blah, blah, blah. The survey also found that men's heights are normally distributed, blah, blah, blah. Before I put any numbers in, I got two choices, so let's see which one they want. Most of the live characters employed at an amusement park have height measurements of minimum of 55 and a maximum of 63. So part A, find the percentage of men meeting the height requirement. So I put in the men's mean 69.4 and their standard deviation 3.5. And then the requirements are 55 to 63. I want to know, my data is that these are the men. I want to know how many men fit between those two. So when I compute, it's 3.37%. Right? Since most men do not meet the height requirements, it is likely that most of the characters are women. Make sense? So real quickly, watch. Let's see how many women make the requirements. Just so we can satisfy ourselves. All I got to do is change these to the women's. The 55 and 63 are still okay. You see, almost 43% of the women meet those requirements, whereas only less than 4% of the men. So that's why we can say most of them will be women. If the new height requirements are changed to exclude only the tallest 50% of men and the shortest 5% of men, what are the new requirements? Well, I got to change it back to the men. And all I got to do is the lower one. So I do standard, and I do less than 5%. The lower end is minimum 63.6. And the upper end is 50%. Well, that's just the mean. So it's 69.4. Because the mean separates at 50-50. So I don't got to compute it. I know it already. All I have to do is calculate the lower 5%, the shortest 5%. Let's do that. Bandwidth, huh?
Always the best.
You see why I didn't have to calculate this one? Because it says 50%. Well, the 69.4 already captures that value, 50% either side.
Okay.
24. A survey found that women's heights are normally distributed and men's height. What percent of adult men can fit through the door without bending? The door is 56.1 inches. It's an airplane, small airplane. So I got to put the men's values in again, 67.8 and 3.8. And then we want, what's the probability that there'll be less than 56.1? It's going to be almost none. Yeah, 0.1%. Right? 1/10 of 1%. Does the door design appear to be adequate? No, it's not adequate, but a much higher door would require major changes in the design and cost of the jet, making the larger door height impractical. That's because the curvature of the plane has to be, it's a smaller circle or oval, so the curvature is set by the fact that it's a small plane. You have a larger plane, the curvature is much less. You can make a larger door. The hinging is just impractical, so that's why they have such a small one. That's the problem. Oh, once again, it's going slow. Have you been on one of those small planes like that? My mom was 5'1", wouldn't affect her. All right. A common design requirement in the environment to fit people who fall between the 5th percentile for women and the 95th percentile for men. In designing an assembly work table, the sitting knee height must be considered, which is the distance from the bottom of the feet to the top of the knee. Males have a sitting knee height, normally distributed with mean 21.1 and a standard deviation of 1.2. Females have a sitting knee height of 19.1 and a standard deviation of 1.1. What is the minimum table clearance required to satisfy fitting 90% of the men? So we want X greater than some number to be 95%. 19.1. Do I have all the numbers incorrect? Yes, yes, yes.
I think you should be looking at the 19.1 as your mean.
That's for women. It says men.
Females are sitting, okay.
We want to fit 95% of the men. I think the numbers are correct. Am I reading the problem? What's the minimum table clearance required to satisfy the requirement of fitting 95% of the men? I'm missing something. Do I have this backwards?
It's 95% should be on the greater than.
Should be where?
The greater than.
No. That's the probability. This is the X value.
I think she's talking about the symbol itself. The greater equals to symbol.
No. This can't be a probability. This is an X value. It's the number from the inches. Am I thinking about this incorrectly?
I think it should be going the other way. I think the white should be on my right channel. This would be 95th percentile, so it'd be that and lower. Not.
Oh, I see what you're saying. Yeah, I got it backwards. Yeah, I was thinking backwards. I'm sorry. I had a.
Doing better.
That's great.
I thought they had a fit in it. It's just that.
We're looking for the 95% that so it will be less than. Oh, okay.
Yeah. Okay, so that's the now. Would this have any? Would the 5% for women be any stricter than for men? No, it'd be automatic. They'd fit automatically because the 95th percentile for men is greater than the 5th percentile for women. That goes without saying. bottom. Okay?
Mm.
All right. That's it. Last one I got stumped on for a little bit there. All right, so you need a break or you want to keep going?
Absolutely. Keep
We
going.
going? We good? Okay. This is called central limit theorem. CLT. And what I'm not going to prove it to you or anything, but X bar, if I take a sample, then a sample is distributed normally with mean mu, and the standard deviation becomes what we call the standard error of the mean. It's divided by the square root of the sample size. So this is the standard error. If you think about it, because if I take an average, a mean value, it's got to be closer to mu.
Correct.
And so its spread has to be smaller. It can't have the same spread as just an X value. By the way, this is the same formula for this, because when n is 1, square root of 1 is 1. So it's the same formula. You could use this no matter when. It's just that for the when we have a sample, then we have to take that into consideration. I'll show you that as we go. The other thing is, when you have a population that's normal, then it doesn't matter what sample size you have, it's going to be normal. It's inherited. If you have a population that's not normal, but you have a large sample, 30 or more, then you can consider it to be normal.
Okay.
It becomes normalized because it's a large sample. Okay. So a researcher collects a simple random sample of grade point averages of statistics students. She calculates the mean of the sample. Under what conditions can the sample mean be treated as a value from a population having a normal distribution? Well, if the population is normal, or if the sample has more than 30 averages. Did I read that right? Well, the researcher collects more than 30 samples. I got it backwards.
Wow.
Oh, there we go. This is the one that's wrong. I picked the population of statistics students. I just saw population. It's the population of grade point averages, and it's 30 or more grade points. There we go. Okay, so it's what I said. I just didn't pick the right one. Number 2. Weights of golden retriever are normally distributed. So right there, boom. Samples of weights of golden retriever dogs, each of size n equals 15, are randomly collected. Is it correct to conclude that the sample means cannot be treated as coming from a normal distribution because the sample size is too small? No, because the population is normal. So it doesn't matter what the sample size is like. Okay. Number 6. So the overhead reach distance of adult females are normally distributed. Did I close it? Yeah, I got to open it up again. StatCrunch. All right, so let's see, stat calculator normal. Their means 197.5, and the standard deviation is 8.9. All right. To find the probability an individual distance is greater than 207.5, so greater than 207.5. 1306. Okay. What's the probability that 25 randomly selected distances is greater than 196? So greater than 196. Only now I got to go up here and change this to the standard error. I divide by the square root of 25. which is 5.
Okay.
So /5. We 0.8003. Right, so you see what I had to do there. I had to go in here and change the standard deviation to the standard error. I had to divide by the square root of n. Since n was a perfect square, I just could go ahead and put the number 5 in there. It's pretty simple to do. And the normal distribution can be used because the population is normally distributed. The original population is normal. All right? And 7. Assume that females have pulse rates are normally distributed with a mean of 76, standard deviation of 12.5. If one adult female is randomly selected, find the probability that her heart rate is between 69 and 83. So between 69 and 83. So 4, 2, 4, 5. Now they're going to ask us for a group of women. So now it's 16 adult females. So once again, they gave me a nice easy number. The square root of 16 is 4, so /4. And it's the same values for x, 69 to 83, and it's going to be a much higher probability. $9,749. Fall asleep, my friend.
I thought
Long day.
Long week.
Why can the normal distribution be used? Because they're normally distributed. Look for that right away. It's the original population. All right. Last one on this. Okay. An elevator has a placard stating that the maximum capacity is 2,052 pounds or 12 passengers. So if you divide 12 adult female passengers, they have a mean weight of 170. That's the average mean weight would be 171. Okay? So if the elevator is loaded with 12 adult female or adult males, find the probability that it's overloaded because they have a mean weight greater than 171. So it's going to be standard. It's going to be greater than 171. So for the men, their mean was 179, and their standard deviation was 32. And I got to do the standard error because the 171 is the average of 12 men. So here's what I got to do. I got to go slash, and you can do this parentheses. Well, if you want, parentheses 12 caret 0.5. There's no square root symbol. I have to use the 1/2 exponent, 12 to the 1/2, which is square root. And so the probability is pretty high. You could tell that because if the load limit's 171 for 12 passengers on average, and you got males that are on average 179, chances are they're going to be overloaded. That's why 1 or 2 guys would step off, make up for that difference. So the probability it's overloaded if you put on 12 men is 8068. 8068. Does the elevator appear to be safe? No. There's a good chance that 12 randomly selected adult males will exceed. See, D says no, they'll always be above the weight limit, but you don't know. You might get some lightweights. But the probabilities, 4 out of 5 is you're going to be overloaded. 4 groups of 12 out of 5 will overload the elevator. All right, so that's it for the central limit theorem. You just have to remember to use standard error when there's a group that you're dealing with instead of an individual. All right, so to continue with the normal idea, we did this before. There's the QQ plots. Remember that name?
Correct.
Yeah, QQ plot. I'll just redo that pretty quick here. 6, 5, 11. So the first one, they give us the raw data. They want us to say, is the normal satisfied? Well, there's not 30. It's less than 30. It's 2, 4, 6, 8, 10, 12, 14, 16. There's 20. So it's not a large sample. So I can't say it's satisfied. I have to see if it fits a normal distribution. And the way we do that is we load this into StatCrunch. You might remember us doing this. It's called the QQ plot. So there's my data. So I go to Graph QQ plot. I select the column that the data is in, and then I also take correlation and normals. I want the normals on the normal means the z-scores. I want the z-scores on the vertical axis. That puts the x-scores. So what this does is it compares z's and x's on a graph, and if they're close to the line, if they're close to this red line, then they're okay. So this one looks pretty okay. They're reasonably close to a straight line. That's my opinion. And they agree. Okay. But it's not always true. Here's one where we have to do the same thing again. Open the data. Now this one has 4 times 2, 4, 6, 8. There's 40. All right, so we could consider it to be normal, but let's see what happens. I open the data in StatCrunch. And do a graph QQ, variable 1, correlation, normal on the Y, compute. And looks pretty good. The correlation's really high, 0.995. Which one does it match? It matches B, right? And I would say, yeah, the distribution is normal. They're reasonably close and do not show a symmetric, a systematic pattern. It's not straight line. I would say yes. Okay. And then last one, here's 50. Actually, I think I did one too many. If we could just do this one. Let's go ahead and open the data again. And close that. Let's see, how many are there? 2, 4, 6, 8, 40 again. 40 should be a large sample, but let's see what the graph tells us. H's, correlation, normal, compute. Now this one you can see that you see the bend in it?
Yeah.
It's a D, right?
Correct.
There's too many that are far away, so I would say D. It shows a systematic pattern that's not straight line. It looks like a curve. So we're going to say D. Okay, so you get the idea. It's just eyeballing it. All right, so one thing left. This is called the normal approximation to the binomial. The reason we do this is because we didn't have high-speed machinery and we had to use the normal. So I'll show you why we did it. And for your participation in this, sometimes you don't have to. So what I'll do is I'll show you, we'll use the binomial, and if it works, we're done. If it doesn't, then we can use the normal, because we get 3 chances.
Okay.
I don't know about on a test, but I think usually the binomial works pretty well. Okay, so I'll show you what's going on here. So normal is approximation to the binomial number 1. The first thing it has to be true is that both NP and NQ have to be greater than or equal to 5. Oh, continuity correction. Remember I told you when we drew the graph, you go half a unit either side if you want to make an approximation.
Right.
So if I want the probability of more than 3, then that means 4 or more, so that I would go back to 3.5. So it's 3.5 or more, so it's to the right of 3.5. That's called the continuity correction. You see?
Yeah.
Because it's greater than 3, so it's not including 3. So it's including 4 or more, so to include 4, I got to back up a half a unit. So it's from 3.5 and to the right of 3.5. That's called the continuity correction. You'll see how that works when we actually, and then the other thing is, we have to make sure that NP and NQ are both greater than 5. See what that says? If they're less than 5, then you can't do the normal. All right, so the first 0.3 times 14 is 4.2. That's less than 5, so it cannot be used. It's that simple. All right? They should all be that easy. All right, so here, 0.4 times 13 is 5.2. So 0.6 would be 7.8. So they're both greater than or equal to 5. So we can use it. So we want the probability of at least 6. Okay, so let's do the binomial first. So watch. Let's see, where do I go? Where am I going here? Get more help. Stat crunch, there we go. Right, so I'm going to do the binomial first and see if it works. So I do stat calculator binomial. N is 13. P is 0.4. And we want the probability of at least 6. So we don't have to make a continuity correction here. All we got to do is greater than or equal to 6. And it's 0.4256. They want 3 decimal places, so it's 0.426. If this works, then we're done. Okay, so they don't like it. So in that case, what we do is we go to stat calculator normal. Now, the mean is NP. You remember the shortcut for the binomial? It's on your handout. So NP is 5.2. You could do it this way. You could just put 13 times 0.4. You could do it this way. You don't have to put 13 times. See, that's 5.2. Now for P, I'm on the wrong one. I'm on the binomial. My bad. We already did this one. I want the normal. There we go. The mean is NP, so it's 13 times 0.4. Now the standard deviation is the square root of NP cubed. So I do parentheses 13 times 0.4 times 0.6 parentheses caret 0.5. So that's your mean and your standard deviation put into the normal, and then it says at least 6. So continuity correction would be x greater than or equal to 5.5. So the approximation is 433. So I go back and change it to 433. You see, now they like it. They didn't want to. A lot of times they'll take the binomial straight up, so why bother with an approximation? But here they did. So if you look on your on the back of number 6, you have your for the binomial, mean is NP, the variance or the standard deviation square root of NP cubed. That's what you put in here for the normal. And then you have to make a continuity correction. since it said greater than at least 6, that means 6 is included, 6 or more. So I got to back up a half a unit and pick up 5.5. So that's why I put in greater than or equal to 5.5 on the normal. On the binomial, it's a discrete, so just leave it. It's not continuous.
So some question.
You'll see this afternoon, all 3 of them turned out to be. I didn't have to do the normal. Yeah, we'll try the next one. There's a couple more we'll do, and we'll see what happens. 16. Probability of flu symptoms for a person not receiving any treatments, 0.051. In a clinical trial for a common drug used to lower cholesterol, 64 of 1,176 people treated experienced flu symptoms. Assuming the drug has no effect on the likelihood of flu symptoms, estimate the probability that at least 64 people experience flu symptoms. Okay, so if I go to the binomial straight up, then N is 1176, and P is 0.051, and I want the probability of at least 64, so that's greater than or equal to 64. Compute the 4 decimal places, 3147. See, now I took it, so I'm done. But I'm going to run through the other one with you so you see how to do it in case you do have to do it. So for this one, I would have to put in 1176 times 0.051. That's the mean, NP. And then for the standard deviation, I would use parentheses 1176 times 0.051 times the complement, Q would be 0.949 parentheses caret 0.5. I want the square root of that. So you see what I did there? The complement of 0.051. I don't need that parentheses there. There we go. The complement of 0.051 is 0.949. Remember that? All right, and now the continuity correction, since I want 64, greater than or equal to 64, I do 63.5. And the answer we get is 0.3202, which you can see how close it is. These are pretty close. That's why it's a good approximation. But that's what you would have to do if they would have said wrong, okay? Let's see about the next one. I think this is the last one, maybe 17. Oh, I forgot to answer the question. Oh well. I'll answer the next one. 17. When a scientist conducted a genetics experiment with peas, one sample of offspring consisted of 949 peas, with 741 of them having red flowers. If we assume that the scientist did under these circumstances that there is a 3/4 probability, that's the assumption, 0.75 will have a red flower, then we would expect 711.75, that's NP, or 712. So they want to know, is 741 that much higher than what you expect? All right. So if the scientist assumed probability is correct, find the probability of getting 741 or more peas with red flowers. So he had 949, and his probability he assumed was 75%. So what's the probability that he would get 741 or more in the binomial? And that is 0.0146. Let's see if it works. Straight up binomial. See? It works. So you don't have to go into the normal. And now we'll answer the question. Is it significantly high? Yes, because it's less than 5%. They don't say anywhere what alpha is. We assume it's 5% if they don't tell us. So yes, because the probability of the event is less than the probability cutoff that corresponds to the event of 5%. 0.05%. See, this is less than 5%.
Okay.
What's in the tail? And then the last question is, what do the results suggest? Since it's significantly high, it's strong evidence against the scientist's assumption. We would reject that assumption because we're significantly higher than what he expected. Not only are we higher, we're significantly higher.
Okay.
See, if we were in the confidence interval, let me show you what's going on here so you can see. This is what we're going to do next time anyway. If we take the expected value of 711.75, let's say 712 is, they rounded it, and we add 2 standard deviations, what are 2 standard deviations? Well, I got to calculate the standard deviations. Let me clear this. So let me start from scratch here. If I do 749 times 0.75, this is our expected value. That's our mean. And then if I do that number, where's my parentheses? If I do that, that's NP. So if I do NP times Q, and Q is 0.25, and I take the square root, there's my standard deviations. So if I take 711.75 and I add 2 standard deviations, because that's the direction we're going on the upper end, so that's 13.34. I'm well above 738. I'm at 741. I'm outside the confidence interval. That's why we get a lower probability level of 0.0146 than the 5%. We fell out of the 95% confidence interval.
Okay.
You see? That's where we're headed with this. Next time we're going to talk about confidence intervals a little more.
Okay.
All right, last one. I promise. Number 20. I hope it's good. Of 246 some thousand cell phone users, it was found that 47 developed cancer of the brain. Assuming that cell phones have no effect, there is a 0.00024 probability of a person developing cancer. We therefore expect about 60 cases. The reason they say expected, if you take that number times that number, you should get close to 60. Let's see if that's true. 246,447 times 0.000241. Yeah, right around 60, 59. Okay, so that's NP. It's greater than 5, so we know we could do the normal approximation, by the way. Anyway, we're gonna do the binomial straight up and see if it works. So we have N is 246,447. P is 0.000241, but we want the probability that X is less than or equal to 47. I said 4. So that's greater than 5%. So we're not significant. So the media was saying that it's a big deal. So the media is wrong. The media reports are incorrect because one would expect more than 60, and we got 47. We got 47 or less. Okay. See, that's what you do, because you can't just put on one number. You can't say, well, you got 47. We expected 60, but you got to take 60 and then put a spread on it. So where does 47 fall? Well, it falls within the region we expected. So we're good.
Seems easy enough.
Yep.
Well, calculate.
All right. So I would say go with the binomial, and if it works, do it. If it doesn't, then use the. Now I did 8 of these. I did 4 by myself and 4 with you. I only had 1 where you had to use the normal. So it's possible you could get by with at least 3 of them that are okay. It just saves you some time. Any questions?
No.
All right. So I'm going to close up. Let me stop the recording.